Welcome everyone. We are happy to have Christian Ferko from Northeastern University and Institute for Artificial Intelligence and Fundamental Interactions. He's going to tell us about his work on neural networks and quantum field theory.
Great. Well, thank you very much for the introduction and the opportunity to speak about this work. It's good to be back in Chicago after, I think, 4 years since my thesis defense. Not much has changed with the building, but it's always good to be around. And I'm going to tell you about this work that should appear later this week with Jim Halverson at Northeastern that's kind of following up on a research agenda that he's been pursuing for the past few years now about neural networks and quantum field theory. So about half of this talk will be a sort of overview of the program itself, the way that I've come to understand it, and about half of it will be about the paper that's to appear soon, which is specifically about the 1D version of this correspondence, so quantum mechanics rather than quantum field theory. So let me start with some motivation. I mean, this talk is sort of at the intersection between physics and AI, but my motivation is really from the physics perspective. And for me, it's really because I don't understand what a quantum field theory is. So I think we still lack a suitably general framework for understanding the diversity of all of the quantum field theories that we know exist. When one first learns about QFT in a course, one typically defines the objects via things like this, path integrals that involve some local Lagrangian density. And that's great for maybe free or certain weakly interacting quantum field theories. But as we've come to learn, this description is not sufficiently powerful for many reasons. One of which is that many QFTs have no local Lagrangian description. It might even be all but a set of measure 0 do not have such a description. The opposite problem is that some theories seem to be described by multiple Lagrangians due to dualities. So in that situation, none of the Lagrangians can really be fundamental if there's many equivalent ones that may have very different degrees of freedom. And a third more technical question is from the mathematical perspective of maybe constructive quantum field theory, that even if you do have a Lagrangian, maybe that is enough to specify the classical dynamics of the theory, but to really understand the quantum field theory, one should also define this path integral measure. And except in cases like free theories or certain super renormalizable theories like phi-4 theory in 3 dimensions, we don't have a general way for doing that, for defining that measure. So these issues and maybe some other issues motivate us to develop new techniques to try to understand quantum field theories. And the specific toolkit that I'm going to discuss and try to apply to this problem is that of neural networks, which has been useful in many other domains of science and mathematics. So going to neural networks might seem like a bit of a non sequitur. I mean, it seems like a priori that may have nothing to do with the quantum field theory. So let me first give you a sort of cartoon reason why you might expect neural networks to be helpful for this. So in a very loose sense, the path integral as we envision it now, is asking us to integrate over functions or field configurations. I mean, really they're distributions, but as a first approximation, let's think about integrating over functions. So the reason why you might expect neural networks to be useful for doing such an integral over functions is because in a precise sense, every function can be approximated arbitrarily well by a neural network. And the oldest example of this, although there's many generalizations, goes back to a theorem of Ferko. The statement is that if you have any continuous function restricted to some compact subset of RD, and you have some error tolerance epsilon, you can always find a neural network with a single hidden layer. I mean, these words really are just shorthand for this function. So there's a particular function that just involves matrix multiplication of the inputs by some weights. The W's are called weights, and shifted by a vector of biases called B, fed into some nonlinear non-polynomial, in fact, activation function sigma, which in the original work of Ferko was a sigmoid function, 1 over 1 plus e to the minus x, but you can pick many other such functions. And then at the outer layer, there's another multiplication by some weights and another bias. So that's what I mean by a neural network with a single hidden layer. It's just this function. There always exists a neural network of this form with the property that the supremum of the error between the output of the target function and this neural network is upper bounded by your error epsilon. So in some sense, this is telling you that you can hit any function that you want arbitrarily well with a neural network of this fixed architecture. So I'll use the language architecture to refer to the functional form of a neural network, which here is this thing. So the heuristic idea is to think, well, if we would like to integrate over functions in something like a path integral, and you can approximate functions arbitrarily well by neural networks, can you replace a path integral with something like integral over neural networks? That's the rough intuition. Yes.
Why would that, I mean, there are many bases of functions for which I could have given the exact same motivation, right? Like
Yes.
functions are also approximated by polynomials or any other set which in the limit becomes complete.
Yes.
So why wouldn't we have said, well, maybe we should approximate the path integral by integrating over the coefficients of polynomials?
Right. Yeah, so you have many choices, but as we know, different choices for the basis of functions can be useful for different things, right? Sometimes you prefer to use polynomials, sometimes you prefer to use a Fourier series expansion. This is indeed just another basis for the choice of functions, but because there's a literature on neural networks in the formal AI field, you might hope that because this is a basis of functions that in physics we don't use very often, that one can leverage different results or use results from the neural network literature that give you additional analytic control. So the motivation is really that this is just something different which we haven't thought about and for which you can import tools from AI.
And then the second question is about the word basis. To what extent is this approximation unique?
Good, yes. So for this particular choice of architecture, if you fix the activation function sigma, I think there's a unique sequence. I mean, this approximates a function arbitrarily well. So if you imagine training this to minimize.
Is there like a unique choice of W's and B that do that or not?
Yes, with this architecture, but you could change the architecture as well. So for a different sigma, there's a different collection of weights and biases. And you can use different architectures that have, say, multiple layers and things like that. But if you fix an architecture, there's a unique trajectory through the choices of W's and B's that's going to approximate these functions, a given function. Yes?
We need to worry about the fact that this is a theorem on a fixed compact set, because I believe one would imagine that when you're doing path integral, you might actually have to consider field configurations which are non-trivial outside of some compact set.
Yes, good. So indeed, this is an issue, this compact set thing. You can imagine taking larger and larger compact sets, and then you might need more and more resolution in the sense that you need a larger network, say a larger N, or you would need more information to approximate this well for some fixed tolerance as you make this set larger and larger. So in the back of my head for this entire talk, I'm kind of thinking of putting in an IR regulator or maybe putting spacetime on a torus or something like this so that I don't have to worry about this when I have to go to large volumes. Good. Other questions?
Okay, so you can parameterize functions this way. You now need some kind of measure on that space, do the path integral?
Right, good. So it does seem like we're pushing back the question by one step, right? Because rather than defining the path integral measure, you now need to define a measure on this space of functions. That's right. So what will replace the measure for us will be a probability distribution over these parameters. And for any finite neural network, this is just an ordinary probability distribution over finitely many random variables for which you can do Lebesgue integrals, ordinary Lebesgue or Riemann integrals. So the question, I mean, this is again like a cartoon, but the question is, can you find such joint probability distributions over parameters which approximates something like a path integral measure in a useful way? I've not convinced you of that yet, but that's the goal. Yes.
Say we are dealing with gauge fields,
Mhm.
then is this architecture like should I say respect? Like does it respect the gauge invariance? Like if you make some smart choice, or what I'm worried is that once you fix to this unjust, like do you in principle have to worry about gauge invariance?
It's a good question. So in this talk, I'm restricting to scalars. I'm kind of taking the Coleman type attitude that to understand quantum field theory, the essential features are already there for scalars as opposed to gauge fields. We have some ideas for how one could implement gauge theory using neural networks. For instance, using equivariance. There's equivariant neural networks where you can try to build in gauge invariance from the beginning, but none of that will feature in this talk. Good. Any other questions? Okay. Good. So let me draw a picture. I think I'm legally required in a neural network talk to always have a picture of a neural network for anyone who's been living under a rock and hasn't seen this. This is an example with multiple hidden layers, but the visualization that we have in mind is that a neural network is always some function from a collection of inputs, maybe n inputs to k outputs, with the property that you, at each step of the neural network, you multiply each of the neurons, these dots in the previous layer, by some fixed numbers called the weights. You then take those linear combinations and feed them into the neurons of the next layer, where you apply some function, which could be the sigmoid function or it could be something else. You might add a bias to the input of that function at each layer. Those are the B's. And then you iterate this procedure. So then you again take linear combinations of all of the outputs of those functions and feed them into new functions, perhaps with additional biases, and you do it again. And eventually you collapse this to an output layer. So this architecture is called a fully connected feed-forward network. In a few slides, going to generalize our notion of neural network to allow other architectures, but this is an example to have in the back of your head as a sort of conventional neural network of the form that we typically put on a computer. And in particular, I just want to emphasize that this approach of neural network field theory is not latticizing anything. So we're not putting space-time on a lattice. We're not discretizing space or time in any ways. So the nodes or neurons of the neural network are not associated with space-time points. We're thinking of these as continuous inputs that label where I am in some space-time and continuous outputs that are the value of a scalar or a collection of scalars. So this is really just a way of describing functions. There's no discretization at this stage.
How are you gonna enforce locality in the field theory?
Good, that's an excellent question. So a priori, a given neural network, you have no reason to expect to be local. What we'll do eventually is try to find constraints on the distributions of the weights so that the correlation functions computed with the neural network respect all of the Osterwalder-Schrader axioms. So this is when you have all of these axioms satisfied, you're guaranteed that you can reconstruct a Hilbert space for a Lorentzian theory that obeys the Whiteman axioms, which Clay was complaining about at lunch, and which has some notion of locality, of local interactions. That will be one of the things we need to engineer, indeed. Good. Okay, so for those that may have thought about neural networks in other contexts, I just want to emphasize what aspects of neural networks I am thinking about and which ones I am not in this talk. So there's at least 3 broad subtopics about neural networks that one could think about. One of them we've touched upon, which is expressivity. How powerful is the network in the sense of its ability to approximate functions? And at least in the case of a single hidden layer, the expressivity question is answered by Sabenko's theorem that we saw. But you could ask these questions about other architectures and ask how well you can approximate functions and so forth. That's one question. The second question is about the statistics of neural networks when you have ensembles of networks that have random parameters. So in the previous example, the parameters of the network were the weights and biases. So they're the numbers that you tune in order to get different functions approximated by your network. And you could ask, given a particular probability distribution for those parameters or weights, what are the properties of the outputs of the function? So that's statistics. The third thing, which I'll say almost nothing about, despite the fact that it's been the source of much of the progress in applications of neural networks, for instance, LLMs, is training. So training is the question not about one particular distribution for the weights, but about time evolution. If you tune the weights so that these parameters change over time in order to minimize some loss function. So this is an interesting question. I'm not going to address it at all. I'm always going to think about a particular fixed probability distribution for the parameters rather than a time-dependent distribution as you train. But you're welcome to think about that fixed parameter distribution as coming from whatever you like. So you can either think of it as arising maybe from some training procedure which is not specified that gives you some distribution at finite training time, or you can think of it as an initialization step. So at the beginning, you generate an ensemble of neural networks with different parameters, and you can think of that as where this distribution comes from. You can think of it as coming from wherever you like, but I won't discuss the details of any particular training procedure at all. So I'm really focusing on 2 and its relation to quantum field theory, or in the third part to quantum mechanics. Okay. So that's the first part, the introduction to motivation. The goal for the rest is to explore the conditions which answer some of the questions that have already come up, the conditions under which the statistics of neural networks can reproduce features of quantum field theories, in particular, correlation functions of local operators in conventional quantum field theories. So I'll say a bit about that, some generalities of what can happen when you consider neural networks under different circumstances and in different limits, which may or may not have the features you would expect for such correlation functions. And then I'll step back and say, well, the simplest case in which one can do this is in one dimension in quantum mechanics. And there we'll see that you can essentially do everything. Yes?
How much is this formalism far away from simulating QCD?
It's very far at the moment. That would be a sort of long-term goal to replace something like lattice QCD and have an orthogonal way of simulating these things. At the moment, we can simulate any 1D system you like. So quantum systems like Schrodinger problem with the general potential you can solve. You can cook up more exotic models, which I'll briefly touch on at the end, which are transformations of conventional quantum models. Everything in 1D is under very good control. To do something like QCD, you would have to overcome some other hurdles, like this question about gauge invariance that we had and other things that we haven't done yet. It's a good question.
But simple models in 2 dimensions, like the Ising model.
Good. So we haven't done that, but that's on the list. I think that's something that should also be tractable. Good.
Because in 1D, you can just use quantum mechanics. You don't need quantum built in the 1D problems.
That's right. So yeah, 1D is just, if you like, Euclidean quantum mechanics, or even you could think of it as just a statistical model. So there's plenty of techniques for studying theories of that form already. We're not claiming that this method of doing quantum mechanics is, it necessarily allows you to do anything that you couldn't do before. It's really a sanity check that if I'm going to convince you that using neural networks might be useful for quantum field theories, as a 0th order statement, you had better be able to do quantum mechanics and do everything, right? And I think we can. Okay. Any other questions or comments before jumping into some generalities? Good. All right, so let me make some general statements, and much of this comes from the earlier papers by Jim and collaborators a few years ago, but with maybe a slightly different perspective. So I'm going to generalize a bit what I mean by a neural network in this talk to allow other architectures. So I showed you a picture of a fully connected feed-forward network a few slides ago, but for the rest of the talk, when I say neural network, I will just mean any parametrized family of functions, which I'll write as phi sub theta from NERN to Rn. The theta indicates that these depend on a set of parameters, theta, which we view as random variables. So the thetas are random, they're drawn with some probability distribution, and when you do a particular draw of the parameters, you therefore get a particular random function. So the statement is that the function phi theta inherits randomness from the random variable phi, or a collection of phi. In general, there can be many, infinitely many, whatever you like. So a simple naive example is just something like a cosine with a randomly chosen phase shift. So my tilde will always mean drawn from. So here theta is drawn from a uniform distribution on 0 and 2 pi. And you can see that this is a random function in the sense that when I draw a particular choice of the phase shift, say theta equals pi, that gives a specific instance of this neural network, which is here just phi pi is cosine of t plus pi. So draw random parameters and get a random function. This looks slightly different from the picture that I drew before, but it's essentially the same thing. This is like a 1 neuron neural network with a cosine activation function and a bias, since the bias is what you add to the input. So it's essentially what we were saying before, but if you'd like to map this language onto the picture that we had a few slides ago, the parameters, the thetas, the things which are random in the previous example were the weights and the biases at each layer of the network. So if you draw those randomly, you get a random neural network. And the question is about the statistics of the outputs of those neural networks as you consider ensembles with different choices of the parameters. Okay, so the way that I think about this, which might be more familiar, is that a neural network I really think of as a 0-dimensional quantum field theory, at least in the way that I've presented it so far. And the reason is the following. So if I have a neural network architecture, so again, the architecture is this functional form phi theta for the outputs of the function, and a distribution p of theta over parameters, I can write a formula that looks like correlation functions in a field theory. So I can write an expectation value of a product of phi's, which really just means an ordinary Lebesgue or Riemann integral over thetas, which I take to be real valued, with some parameter density p of theta and a product of the phi's. But this is really a zero-dimensional field theory because the fluctuating objects, the things in the path integral, if you like, are just numbers, right? They don't depend on any space-time point. So if we just replace the p of theta with some e to the minus s in Euclidean signature, this is really like a quantum field theory where I'm just integrating over numbers with some function weighting the numbers, right? So this is like a zero-dimensional QFT path integral, compared to, say, in 1D, where you integrate over objects that depend on one time coordinate t, which we think of as paths, or in higher dimensions where you integrate over field configurations, which are really distributions, but I wrote here functions, that depend on multiple space-time coordinates. So this is a 0D field theory. And from that 0D perspective, you could ask, what are these objects, these correlators? And since the fluctuating objects, the random things are really the thetas, those are the fields, these objects Gn are really just observables in the 0D theory built from the fields theta in some complicated way, depending on phi theta. So they just depend on some auxiliary variables xi, which are not fluctuating, and you're computing some expectation value of these observables in 0D. So if you like, it's a bit like a matrix model. If you think of the thetas as being assembled into a matrix, this is really a 0D theory in the sense of a matrix model where you could choose a parameter density that's like e to the minus trace DD dagger or something like this. That's all that we're doing. So a neural network is a 0D field theory. That's not especially satisfying because we would like to, yes?
Can you comment on the Hilbert space of the theory? Is it one-dimensional, like the IAIFI matrix model?
Good. Okay, so right. To construct the Hilbert space, yeah, this will be a point that we come to a bit later, but our goal will mostly be to engineer these 0D field theories that actually reproduce the behavior of higher dimensional field theories, right? So in those cases where these are engineered not to just be observables in the 0D field theory, but to reproduce some correlators in quantum mechanics or in field theory, then you can construct the Hilbert space using Osterwalder-Schrader reconstruction. So there you have an explicit map that does this. I guess I shouldn't say explicit, it's rather non-constructive. But those are the cases in which we're going to care about the Hilbert space. In the more general 0D case, I never speak about constructing the Hilbert space. Good. Other questions? Okay. All right, so in a sense, the question I'd like to try to answer, I think the key question of neural network field theory is to say, well, if a neural network is a zero-dimensional field theory, when do you grow dimensions? Where by grow dimensions, I mean the following. Under what conditions do these observables Gn, which were just, if you like, complicated field redefinitions of the fields theta of the 0D theory that depend on some x's, that a priori I have no reason to expect are space-time points, but you can ask under what conditions do those observables actually reproduce correlators of a Euclidean QFT in more than 0 dimensions? That's really the question, because you can only really speak of this as being a neural network field theory when it grows a dimension in this way. In some sense, this is the opposite problem of dimensional reduction, right? You can think of cases like BFSS, where you can reduce some higher dimensional theory down to a 0-dimensional description. In those cases where you have a dimensional reduction, you know that your 0D theory came from a higher dimensional theory upstairs. And here we're asking the inverse, given a general 0D theory parameterized by neural networks, when does it come from something upstairs? And what I'll focus on, as I mentioned before, we'll ask when these GNs satisfy these Osterwalder-Schrader axioms. So in these cases, you can do a reconstruction of a Lorentzian Hilbert space from the Euclidean correlators. There's actually 5 Osterwalder-Schrader axioms. 2 of them are not so interesting for us, but the ones that we care about are these 3, which are Euclidean covariance, which says that the correlation functions have to transform in the appropriate way under rotations and translations. For me, I'm focusing on scalars, so these have to be scalars under such transformations. You need a cluster decomposition property so that if I have a collection of p points that are far away from some q points, then correlation functions factorize in the limit as I take those points far away. And most interesting and subtle is this property of reflection positivity, which I'll have more to say about. But this is essentially the statement that certain Euclidean correlators that compute norm squares, these sorts of objects, Rossi-Ketzai in the Lorentzian Hilbert space need to be non-negative in order to avoid the existence of negative norm states. And we'll have to engineer all of these explicitly in order to get genuine neural network field theories. Okay. So you might ask, are there any examples that are known where you can point at something and say, this is something like a neural network field theory, and you can have an explicit case where this growing in dimension happens? And I claim that we can really just reinterpret an existing result from the constructive QFT literature and say, here is an example where that happens. So if you open a book on constructive field theory where they build the Gaussian free field for you in d dimensions, this is just a free scalar field in d spacetime dimensions, Euclidean. They will write formulas like this, where they say we're going to consider really random distributions, but they write a formula like this, which defines a scalar field as a sum of random orthonormal, or sorry, non-random orthonormal functions. So the FK are deterministic. These are a basis of functions on a domain in RD, and they come multiplying IID random variables that are unit normal. So you write a formula like this. This is a collection of Gaussian draws multiplying fixed functions. So although this is well known, I'd like to interpret this as a neural network according to the definition I gave a few slides ago. Since I said any parameterized family of functions that has some random parameters theta is a neural network, this formula really is a neural network with infinitely many parameters theta k that are just IID normal Gaussian. So this is one explicit example where something which satisfies our definition of a neural network actually allows you to define a free massless scalar in d spacetime dimensions. And that at least is a proof of concept that a neural network can mock up the behavior of a higher dimensional field theory, right? Even though I said we're thinking of this as a 0D field theory, here the degrees of freedom of the 0D field theory reassemble into one scalar degree of freedom in d spacetime dimensions. So this is just to convince you that this possibility is not crazy. Okay. So it seemed important in at least that example, and you might have expected on general grounds that since quantum field theories in 2 or higher dimensions have infinitely many degrees of freedom, you might expect that whatever you would like to do to engineer neural network QFTs, you had better have infinitely many parameters. So I think that's true. So you might want to classify what are the possible behaviors that can happen in a neural network as you take infinitely many parameters. And this will let me review some of what was known about these limits in the earlier papers from a few years ago. So several things can happen. I'm going to focus on 3 cases of interest. So one, which was the focus of many of these earlier papers, like this one by Jim and collaborators 5 years ago, are so-called Gaussian process limits. So this is an infinite width limit, which I'll show you. And essentially by the central limit theorem, these limits lead to neural networks with multivariate Gaussian distributions over the outputs. So I'll explain that in a moment. That's one thing that can happen. A different thing that can happen, which is the subject of the paper that should appear this week, is what I call stochastic process limits. So these are 1D quantum models, so functions from R to R, which we write as real valued functions with random coefficients, a bit like the expansion on the previous slide. And generically, those expansions lead to stochastic processes, which are random functions that are continuous but differentiable nowhere. And those are exactly the sorts of functions on which the usual quantum mechanics path integral measure is supported, right? We learn in quantum mechanics that we integrate over paths, but the rigorous definition of the 1D path integral measure goes through this Wiener measure of mathematics, and the Wiener measure is supported on differentiable nowhere paths. So I'll tell you that we can realize all of those with neural networks. There's a universality proof. And the third case, which has to do with the higher dimensional example, are distributional limits. So there are neural networks where you take an infinite parameter limit and you can just prove that almost surely in that infinite parameter limit, the neural network gives a divergent output for any input x. So these are not actually defining functions. They diverge everywhere. But despite that, if you choose the architecture appropriately, in these limits, you can integrate the neural networks against appropriate test functions. And that sounds like precisely what we expect to happen in quantum field theory, where the fields are really distributions. So these limits, which will be the subject of a follow-up paper that will come out after the quantum mechanics one, these allow us to actually define Euclidean QFTs. And if you engineer everything appropriately, you can satisfy these Osterwalder-Schroeder axioms. Okay, but here this is sort of going up in complexity or in dimension, if you like, since I'll argue that these Gaussian process limits look like field theories, but are still secretly zero-dimensional theories that have not really grown a dimension. I'll explain that in a moment. So this is in some sense 0D, this is 1D, and this is a higher D field theory. Yes?
Regarding the infinite many parameters, what is their physical interpretation?
Yeah, good. I mean, I would think of it as, if we think of like the dimensional reduction example, for instance. So the infinitely many parameters I think of as the fields in the 0D model. So if you view it as starting with a higher dimensional field theory, say on a torus, and reducing, keeping all of the Fourier modes along the torus all the way down to 0 dimensions, then I would view the thetas as the Fourier coefficients for all of those expansions along the torus direction, right? So you're coming down from a field theory in higher D to an infinite collection of 0D fields in such a way that you hope, in this case you know, came from a higher D field theory. So roughly speaking, you can think of the thetas as some generalized Fourier coefficient from upstairs. Good. Other questions? All right, so let me explain this limit from the earlier work and why I think it's interesting, especially in the physics for AI direction, but why I think it's not giving us the field theories that we want. Okay, so this is a summary of something that's known, this so-called neural network Gaussian process correspondence. And the simplest example I can give you to illustrate this is the architecture we had before, which is a single hidden layer. So we have a function phi theta that up to some normalization is a sum of these matrix multiplications of inputs fed into some activation function and then multiplied by some other weights. I've turned off the biases for simplicity, but you can turn them back on. It just makes the story slightly more complicated. And in this neural network, the parameters again are just these weights. So the wij0 and the wi1. And to take this limit, I'd like the weights to be independent and identically distributed. So the statement is that in that context, with IID weights, you can prove, which was done by Neil, I think in the 90s, essentially due to the central limit theorem, that as you take an infinite width limit, so remember n is the number of neurons in the single hidden layer, as you take that n to infinity, which is an infinitely wide network, this random function, so the outputs of this function are of course random variables with some distribution. You can ask, what is that distribution? And the point is that in the limit, that distribution approaches what's called a Gaussian process. So that's, I'll define it precisely in the next slide, but the statement is that the outputs of this function are always distributed according to a multivariate normal distribution with some mean and some kernel. And you can compute these mu and k explicitly from the PDF of these weights. So these guys are IID according to some probability distribution. If you know that probability distribution and take the limit, from it you can compute this mu and this k, some formula. Okay, so there's a nice picture of this, if you'll indulge
What's the
me.
dependence on X?
On X, sorry, let me go back. Yeah, good, sorry, it's
Like, does it depend in any way nicely on X, the answer, or not?
yeah, so it does. So the X goes into the mean and the kernel. So for one X, if you like a 1-point function, then it's essentially just a Gaussian distribution where the X appears in the Gaussian weight. If you have a 2-point function of a collection of 2 of these things, then it will depend on the X and the Y in some way that we can write. I'll show the formula on the next slide, which makes it clear. Yeah. Okay, so let's just look at the picture. I think it's instructive. So this is a nice animation of this limit. Let me pause it for a moment. So what's happening here is, in this case, a 2 hidden layer network, but we're going from bottom to top. So we feed in 3 inputs at the green nodes, and we do this process I've been describing of multiplying by weights, adding biases, and so forth. I think here the biases might even be non-zero. You repeat, and then there are 2 outputs. So if those parameters are random, the outputs y1 and y2 are also random variables, and you can ask about their probability distribution. And the claim is that here, where there's, say, 4 neurons in each of the hidden layers, the probability distribution over outputs looks quite jagged and horrible. But as you add more and more neurons in the hidden layer, which it shows here, you add some more and things start to smooth out, and you add more and more and more. And eventually, if my computer doesn't die, okay, it lagged a little bit. Eventually you approach this Gaussian distribution over outputs. So this is at fixed x. I'll show you the dependence on x in a moment, but at fixed inputs, the distribution over outputs in this infinite width limit approaches this multivariate normal distribution, like a Gaussian. So it smooths out. This is the statement of neural network Gaussian process correspondence in the infinite width limit. Okay, I haven't actually defined for you what a Gaussian process is and what the dependence on the x's is, so let me just do that. More precisely, if you haven't heard this before, a Gaussian process is just a family of random functions phi theta of x, so that for every finite set of inputs, if I take the probability distribution of all of the outputs phi theta at each of those inputs, this thing is a multivariate normal distribution. And more explicitly, it's easy to describe this in terms of the characteristic function. So this is essentially the Fourier transform of the probability distribution. But the statement is just that this family of functions is a Gaussian process if, that's what the exclamation point means, if the expectation value of this e to the I sum of the phi theta of x's takes this particular form. So this is why it's called Gaussian, right? It's an exponential where there's a quadratic piece that depends on the kernel k, which is a function of the two inputs, the xi and xj. You sum over the i's and j's. And then there's a mean piece that is the sum of the mu, which is a function of the x's, evaluated on each of the inputs. So that's the dependence on the x's. They go explicitly into these two functions, the mu and the kernel. Okay, so that's a Gaussian process. And this really looks like a field theory. So this looks like the sort of thing that we do in Peskin and Schroeder. So for simplicity, if you turn off mu, which is like turning off the sources, this is like a source-free free field theory that has some action that looks like this. So the kernel appears in some way, and you have two phi's. So it's a quadratic action, which is why you're thinking of it as Gaussian. And the inverse of the kernel is just defined in this way, as you would expect. That integrating the inverse against the kernel with one shared argument gives you a delta function. Okay, so this is the Gaussian process limit. You might say, what's wrong with this? This seems great. It seems like we already have QFT-like behavior already by taking an infinite width limit. And in some sense, that's true. This is what a lot of the early papers were thinking about. And these are interesting models. But I'll point out one issue, which is just that all moments of a Gaussian distribution you can prove, essentially because of the exponential fall off, everything is smooth enough so that moments are finite. All moments of a Gaussian distribution are finite for any values of the inputs. So for any Gaussian process, for instance, if I consider the 2-point function at coincident points as y goes to x, this will always be less than infinity. You always have finite endpoint functions as any pair of points become coincident.
Sorry, but in your discussion, you only had a finite number of inputs, right?
Yes, but you can do it for any finite collection of them. So for every finite set, you can do it for any choice. But once you fix a choice, this distribution is always Gaussian, right?
Right, but I was just thinking, this limit that you were talking about was the number of possible x's was fixed and the network in the middle got very wide. But to discuss, continuity as x goes to y in the 2-point function, don't you need a kind of continuously infinite number of inputs as well?
Yes, so the inputs can be any real numbers, right? So it's not like there's a library of possible inputs and it's a finite number of x's and you can only pick those x's. All of the x's can be any real numbers. It's just that once you've made a particular set of choices for those inputs, which are all real numbers, then the distribution over outputs looks like this. But the x's can be whatever you want. So in particular, you can see from this that if you know what these functions k and mu are.
Well, what are the functions then, k and mu?
Yeah, they're fixed by some formula which I haven't written in terms of the distribution over the w's, right?
But you can write such a function? You can write, one knows this function?
Yes, yeah, you can determine it from the piece here, right? And given those, you can look at continuity and limits. You can take these points coincident, for instance. Good.
Follow-up question. What is this K function relative to the free field theory limit? You know K for the PFT case, what is K relative to?
Are you asking about the interpretation of the K or?
I'm trying to compare the K from quantum theory relative to the K that you're getting when you're saying is fixed by this requirement.
Right, yeah, so you can, I mean, K here is essentially the field theory propagator, but I guess you're asking how do I compare the actual value of the K to what the K would be for an actual field theory propagator? And the answer is that although I said K is determined from the probability distribution over weights in some way, you can prove that given any distribution of weights, the K that comes out will have certain properties. You can prove that Gaussian processes always have kernels with X, Y, and Z properties, and one of them is finiteness, right? So you can get essentially any K that you want modulo these restrictions, but the killer restriction is that you can never choose any probability distribution over weights, which will give you a K such that 2-point functions diverge at coincident points. That's the problem, right? Otherwise, if you allow it to be finite and have appropriate fall off and so forth, I can always find some probability distribution over weights that engineer that kernel in the infinite width limit.
The issue is that you require the same sigma for each I. If you
Good.
allowed sigma to depend on I, it would just reproduce the same expansion that we usually do, right?
Good. We do, let's see. We do restrict it to be the same sigma everywhere. I actually don't know what happens if you allow the sigmas to vary.
Well, I mean, if you took J to be 1 and had sigma was allowed to depend on I, you could just take sigma I to be a basis, and then you would just have the standard expansion of phi. In that case, you could probably get whatever K you want. At least you can
Good.
kind of tautologically reproduce the field theory K.
I see. Okay, so you say you can just cook up by hand a collection of sigmas in order to reproduce this. Yes, okay, I think that's true. Okay, I think, yeah, good. I think that's essentially, yeah, that might be related to what we actually do in the quantum mechanics and field theory cases. It looks slightly different, but indeed, the neurons are different in the cases where we get field theory correlators. That's right. Good. So maybe that's one interesting way to think about it, is that here, the restriction of the identical sigmas is what's preventing you from mocking up field theory behavior. Yeah, need to think about it, but it sounds right. Other questions? Yeah.
Two related questions. One is, you said X here is a continuous variable,
Yes.
but when you implement this on a computer, you're constrained by, you know, how many decimal points you truncate by.
Yes.
So how can you ever verify, for instance, that you get continuum behavior?
Yeah, good. So if you use floating point variables, then indeed there's some error bound, but you can test it. I mean, you can imagine, for instance, taking a sequence of models where you include more and more decimals and asking, is this becoming a better and better approximation to some continuum function, right? So you never genuinely get honest, real valued quantities when you implement this on a computer, but the claim is that as you improve the accuracy, you can approximate continuum functions arbitrarily well, right? That would be the claim.
The other question is, since you're talking, you want correlators that diverge in the limit of coincident points. But again, you know, you have to, the way you verify that is if you get something that's infinite, but you can't actually program something that gives you infinity on a computer.
Yeah, that's right.
You get very large numbers. That's
Good.
also-
Yeah, indeed. So yeah, there I think I would also make a limiting argument, because even in the field theory case, if you have infinitely many parameters, you're always going to do a finite truncation when you're on a computer and include infinitely many. And I think there, what you would want to do is argue that as you include more and more parameters and then evaluate nearly coincident point limits, that you see that the outputs are growing without bound, right? That they're getting larger and larger. So there's really two separate directions, I guess, in this research program. One of them is purely theoretical, where we write formulas like this and say, consider a neural network with this set of weights and this set of biases and try to prove things about it. And the second direction is really implementing the things, right? So in doing implementations of these field theory things, one would have to address all of the issues that you're talking about, worrying about floating point arithmetic and convincing yourself that you are really getting divergences rather than fooling yourself. That I'm speaking less about, but it's important to address. But at the theoretical level, you can prove certain properties which you believe that if you have a good proof and you implement it correctly, that you should be able to see the appropriate signature, the behavior you produce. Good. Other questions? Okay. So I think I was here. Yes. Okay. Good. So I was flagging for you that these Gaussian processes are not the appropriate limit to take for genuine quantum field theories because of these finite 2-point functions. Since, as we know, if you have any genuine unitary QFT in 2 or more dimensions, the 2-point function of non-trivial local operators, so not the identity, but anything else, when you take the coincident point limit, has to diverge. So this is, you can argue for this in many ways. You can use the Cowan-Lehman representation, or if you want to argue heuristically, you might say that your QFT should be controlled by some CFT in the UV, and if it's unitary, then the 2-point function diverges in this way, where delta is the dimension of these operators in the CFT. So from this heuristic argument, you would say, well, okay, the leading short distance behavior should be controlled by this divergence. However you want to argue for it, I think we need coincident point divergences to have a genuine field theory. Right. So the Gaussian process limit is interesting, but I would say that it's really a theory of random functions, right? Since these are not distributions, they're honest functions in the sense that you can evaluate them on inputs, and a theory of random functions does not have the appropriate divergence structure to reproduce the correlators of a QFT, which we think is reasonable since we believe that the path integral measure at least is supported on distributions. So if you would like some generalization of the path integral measure, which is really what we're trying to do, we're using neural networks to define something like a distribution over functions or generalized functions, then you would expect that also to be supported on honest distributions as opposed to functions. Okay, so this is the motivation for considering different infinite parameter limits besides the infinite width limit. So now there's 2 directions you could go in. So you could say, well, I would like to try to engineer higher dimensional field theories by taking a different infinite width limit. So this I have less to say about, but it will be the subject of the next paper after this, the one that's coming out this week. Instead, I'm going to sort of shift focus and try to just do the 1D version. Since the quantum mechanics case, as I was saying, is under complete control, and I think we can essentially get everything. So in the quantum mechanics case, there isn't a divergence at coincident points. So we evade this issue a little bit, but there are other things that you need, other features you need to have in order to reproduce good 1D Euclidean theories, quantum mechanics theories, like this nowhere differentiable property, which you need for commutators. So I'll discuss that a bit in the last part of the talk. So this is a summary of the paper coming out this week. Before I do that, other questions about the motivation or the hierarchy of different infinite
Sorry, can
parameters?
you remind us, I'm blanking, what is the behavior of the 2-point function in quantum mechanics as the times become coincident?
I can show you here. So in any quantum mechanics theory, the 2-point function essentially has to be some integral over weights of this thing. So this is like the harmonic oscillator propagator. So this is, if you like, the 1D Cowan-Lehman. It has to be this, and
But
this
if t equals s,
t equals s, this is 0.
that integral has to converge?
Yes, because it's required that rho is a normalizable distribution, so it has to be finite in a unitary quantum mechanics theory. That's right.
Okay.
Yes.
Regarding your worry that you get only finite correlation functions, sometimes in quantum field theory, when you renormalize correlation functions, say by subtracting the leading order singularity, you get a finite result. Can you do some kind of match between the result you get for the finite neural network procedure and the renormalized 2-point functions?
Good. Okay, so I guess the question is, can you interpret these neural networks with finite correlators as somehow giving you correlation functions of renormalized fields, which would have been finite? Maybe. No, it's an interesting question.
Renormalized fields don't have finite correlators.
Okay, so I guess the answer is no.
The 2-point function that you showed in CFT is for a normalized operator.
Good. Okay, so we always need divergence, which is what I was.
You mentioned you take CFT and torus, you can renormalize the leading order divergence by subtracting the log least square, and you get a finite piece that you have. This in this particular example.
I don't know, but Clay is shaking his head, so I don't know. Yeah, I guess the safe statement I would make is that if you want to do Osterwalder-Schrader, where you're speaking about, I guess, bare fields, then you need this divergence structure. Maybe you always need this divergence structure.
I think you're thinking of like a CFT or something in the ultraviolet, where you have some universal divergence you can subtract, and then you'll get something finite. But here it wants to reproduce the actual CFT endpoint function.
Okay, other questions?
Okay.
Is there a way to make sense of this things not diverging if you put things on a lattice? Like, can you maybe simulate lattice field theories in this way?
Yes, good. So you can always laticize things. There has been some work on this, on neural network type realizations of lattice field theory. So there you would not have to worry about this. But then you have to deal with the normal issues that you would have to deal with when doing lattice quantum field theory, I guess, right? Existence of continuum limits and things like this. So that's a direction you could certainly pursue. But sort of the hope or the dream for this research direction is that you will have a separate toolkit that does not require you to use kind of lattice QFT or QCD techniques, for instance. So yeah, so we're avoiding a latticization, but that's one way to resolve this. Yeah.
Do you gain anything interesting by going deeper rather than wider?
Good. Yeah. So you might ask, yeah, what is the benefit of depth? Because all of the examples so far were single layer. Good. Most of the universality results allow you to do things arbitrarily well with a single layer, but the issue with these universality results is they're typically non-constructive, so they don't tell you how to actually find the weights and biases with the single layer network that do this. So the advantage of depth, as far as I understand it, I don't think there's a good theoretical control over this, but depth, I think, allows you to more easily find good approximations by training, using, for instance, backpropagation. So that's more of like a in practice operational benefit of using depth. We'll have one example at the end where I'll mention what we call deep neural network quantum mechanics, where we do use depth to mock up new quantum theories. So that's something that we do on a computer, but for the theoretical results, typically one layer is enough. Yes. Good, yeah.
I guess this is a question related to Sal's question, which is, could you imagine taking something like a Tuft limit where you take both depth and width to infinity, but like keep the aspect ratio fixed?
Good. Yes, you can do that. So Cengiz Pelivan at Harvard and with his PhD students have been looking at slightly similar things where you take these sort of what I would call like a double scaling sort of limit. And yeah, if I remember correctly from that work, there's a sort of phase transition where if you take the limit in a particular way, in one direction, the outputs of the network are diverging, and in another direction, the outputs of the network are always going to zero, but there's a sort of sweet spot like a locus where you get nice finite outputs from the network where you have theoretical control over what they're going to be. This is in some sense a generalization of this neural tangent kernel sort of analysis, which you might have heard of. So you can do that, and it seems interesting, but we did not do that. Good. Any other questions? Okay, try to give a flavor for this in 5 minutes. So now I'm stepping back from the QFT. So this is, if you like, a toy example. I guess one of the many things I learned from Saab when I was here, which is if you have some interesting phenomenon you want to study in quantum field theory, you had better first be able to understand it in quantum mechanics if you have any hope of generalizing. So what happens if you try to do this neural network quantum field theory in 1D? And that's the topic of this last part. So first of all, what is a 1D quantum field theory? We've been characterizing our theories in terms of correlation functions. So in 1D, a quantum mechanical model is defined by a set of correlators for what I'll call X. So I'm replacing the field variable phi with X, which I'm thinking of maybe as like the position of, if you like, a quantum harmonic oscillator or something like this. This is the single particle degree of freedom. You can generalize it to multiple X's or in principle to fermions or all sorts of other quantum models, but I'll just speak about one X for simplicity. And the correlation functions look like this. They depend on a collection of time coordinates T, as opposed to multiple space-time coordinates. And the benefit of working in one dimension is that these theories are closely related to the mathematical literature on stochastic processes. So we have a huge collection of results at our disposal. I'm not going to give the modern definition of a stochastic process in terms of the sigma algebra and all of these things. For me, I'll use this more pedestrian definition that a stochastic process is a collection of real valued random variables, which I write as x sub t, labeled by these labels little t in an index set, which for us will be either the real numbers or a finite interval. And in order to define a stochastic process, all I have to do is tell you how to assign to any collection of n variables ti in the index set, and for any n, some joint probability distribution that looks like this. So it's collections of random variables at each of the t's. And again, the t's can lay anywhere in the index set. They can be, for instance, any real numbers. There's not only a finite collection of t's you're allowed to pick, but the joint PDF always refers to a particular collection of the t's, right? You can change this and ask about different t's, but the assignment of a PDF always refers to a particular choice of finitely many. Okay, so this is the stochastic process language is essentially the same, since if you have a PDF, you can always compute correlation functions by taking the mean of the product once you have this joint PDF. So stochastic process is essentially the same object. It's the same defining data, if you like, as a quantum theory. Okay, so then you might ask, well, that's great, but what additional properties should a stochastic process have in order to be a reasonable quantum theory? Since every stochastic process defines a set of correlators, but not every collection of correlators is a good quantum theory in the sense that we learn about in undergraduate quantum mechanics. So here I'll give you a sort of minimal set of conditions, which is weaker than the full Osterwalder-Schrader, but as a zeroth order statement, you might think that your minimal quantum model should have some sort of continuity. The technical assumption from stochastic process land is this notion of mean square continuity, which you can think of as being the statement that the sample paths are continuous. So this is like saying that your quantum particle should not be able to jump instantaneously or teleport from one position to another in 0 time. That's one assumption. And the second assumption is this 1D version of Callan-Lehman, which is really the equality between the far left and the far right side. It's just the statement that the 2-point function admits the spectral representation. But to see why that's reasonable, this is essentially a one-line proof of why there should be a 1D version of Callan-Lehman. And it comes from inserting a complete set of energy eigenstates. So if you do this insertion, you can interpret this as an integral against some measure, some normalizable measure rho, which in this case happens to be given by this sum of squared matrix elements. So these are very minimal. So these are the only two things we need to assume to get one of our first results. If you like, it's just continuity of sample paths and the second condition, which tells us that in quantum mechanics, the 2-point function is always finite, as opposed to in QFT, where it diverges. And already with these two minimal assumptions, there's a nice fact. So one of the results that will appear is that any Euclidean quantum model x of t, which satisfies those two minimal assumptions, admits a neural network description. So there's a particular architecture where for technical reasons, you have to first subtract out the mean, if you like, to get this sum. So you compute the mean of the process, which is a deterministic function, and then you can expand in terms of some random variables theta k times some continuous orthogonal real valued functions. So
How is this different than just introducing a complete basis?
Good, so there's some nice properties of this. So this particular choice that comes from this so-called Kosambi-Karhunen-Low theorem in stochastic processes is optimal in the sense that among all expansions of the stochastic process in a basis, this minimizes the error, the truncation error when you include finitely many terms. That's one nice feature. The second nice feature is that the theta k are, in this case, pairwise uncorrelated, which would not be true for a general expansion. So these are theoretical results that give you better control using the expansion in this form.
If I have some Hamiltonian, standard Hamiltonian model of quantum mechanics, can you say what FK is?
Good. From the Hamiltonian, yes, I think so, because what I would do, here we're in Euclidean, so if what I would say is that you hand me your real-time Hamiltonian, I Wick rotate. I now use the stochastic process description, which allows me to translate from the Hamiltonian to the so-called Fokker-Planck forward operator. This is a well-known thing that you can do. And from that thing, you can understand the statistics of the stochastic process, in particular the covariance operator. And then in the proof of this theorem, you do a particular sort of diagonalization of the covariance operator, and the eigenvalues when you do that diagonalization are the FK.
So it's diagonalizing the 2-point function.
Roughly, yes, yes. It's a well-known procedure that you can do. So it's some diagonalization.
So in a free theory, FK would be the standard basis of like eigenfunctions of the Laplacian.
Yes, so for a harmonic oscillator, for instance, yes, that's right. For interacting theories, it's something else. Good, yes.
In what sense is this just a neural network versus just a basis expansion? I mean,
That's what I was just asking.
like, the neural network I imagine has like some standard structure of like linear, non-linear, linear, non-linear, with like the fixed non-linearities at each step and so.
Yes, good. So, yeah, in some sense, the fact that you can do an expansion is not new. The fact that you can have an expansion with these properties is sort of nice. And rather than using depth, here, all of the behavior is in some sense happening at the first layer, right? This is a neural network with these just orthogonal neurons and coefficients theta k. For a given stochastic process, if you can realize it in this form, you can probably non-uniquely realize the same process in many other ways with deep neural networks that have different lengths, different widths at each layer, and different numbers of layers and so forth. But if you like, this is like a canonical form. So there's many expansions you can have. The statement is just that, you know, for any process that could have many possible expansions, you can always bring it to an expansion of this form that's characterized by these properties that I said. And sometimes it's useful to have a canonical representation. Was there another question?
Yeah, in the previous slide, when you said that when the limit of t goes to s, it's t minus x squared goes to 0. What happens if you put the quantum mechanics in a thermal state and t and s differ by beta? Would this condition be modified?
Good. Okay, so for the thermal version of our story, this is a local property because we're taking t and s together. So you still, in thermal quantum mechanics, want to impose this mean square continuity, but some of the other conditions get relaxed. So for instance, I'll speak about the Markov property. For quantum mechanics on a circle of radius beta, that gets replaced by a different property, the so-called one-sided Markov property on a circle. So if you want to do the thermal case, the short answer is that various assumptions change, but you still want this one, this local property that doesn't see the beta. Good. Okay, well, I think I'm now out of time, so I might, maybe I'll flash the remaining results and then you can ask me more questions at the end if you like. So very quickly, this was this canonical form, this universal representation in a nice way that I was just describing. As a picture, maybe a Venn diagram is useful that within the space of stochastic processes, there's some that you can represent with neural networks. The statement that we described is that if you fix a particular architecture for the neural network you want, that every minimal quantum mechanics satisfying those two assumptions always lies within a space of neural network stochastic processes, because these always admit a representation with a particular canonical form. And depending on who you ask, different people want different things in their quantum models. Some people want Osterwalder-Schrader. Some people might say, well, I don't really want unitary time evolution because I want to study open quantum systems, or I want to relax continuous time translation invariance and study flow case systems, or whatever you like. But the point is that any relaxation that you do, we argue, still lies within the space of minimal quantum modeling. So you can always use this machinery, this canonical representation. Good, so very briefly, maybe I'll just flash how we engineer these other OS axioms if you would like to restrict to this particular subset, the one satisfying full OS, so that you can do reconstruction. Two of the properties you can essentially translate into stochastic process language. So the statement of Euclidean covariance in 1D is just the statement that your process should be stationary and symmetric, which are defined here. Cluster decomposition maps onto a term from the ergodic theory literature called mixing. So if the process is mixing, it cluster decomposes. And reflection positivity is the one that we focus on. So we engineer reflection positivity for the models in our paper using a collection of mechanisms. I'll just tell you two of them. One of them is that if your neural network quantum mechanics is presented, or if your quantum mechanics is presented by a neural network, which as we've seen, all of them can be, you can engineer reflection positivity using what we call a parameter splitting mechanism. So if you make some assumption about the neural networks where the parameters decompose in a particular way, so that roughly speaking, the behavior of the network only knows about some subset of the parameters theta plus at positive times and a different subset at negative times. If you do this decomposition, then you can just write the formula for the object that should be positive in the reflection positivity condition, and it becomes a perfect square. This is one way of engineering reflection positivity. A second way is to assume that the stochastic process is Markov. It's been known actually since some of the early work of Nelson and Osterwalder and Schrader that even in the field theory case that there's a Markov assumption that applies or implies reflection positivity. So this is known. we present a streamlined proof that's easier to understand in 1D, that Markov implies RP. But really, the reason that we're interested in the second statement is to use Markov processes as inputs to come up with a larger class of quantum models. This is the last thing I'll just briefly tell you. The process of being Markov is extremely fragile. Linear combinations of Markov processes aren't Markov, and applying deterministic functions to a Markov process do not preserve the Markov property. But we prove in this paper that if you take any random function, it has to be bounded, but any random function that could, for instance, be realized by some neural network architecture, and you apply it to a reflection positive stochastic process, it preserves reflection positivity. So this gives you a way to cook up new quantum mechanical models. What you can do is take processes that you know are reflection positive. So for instance, Markov processes, you take a bunch of them, you feed them into some neural network, which could be whatever you like, and you are guaranteed that the output of that neural network also gives you a reflection positive process. So this gives you a way to engineer new quantum models that you're guaranteed can be continued to real time and give you unitary systems. And we do some examples in the paper. I'll just show you quickly a plot. Here's some fun example where we take, in this case, we take 3 so-called Ornstein-Uhlenbeck processes, which are the unique stationary symmetric Gaussian Markov processes. They have 2 parameters. We take 3 of them with different values of the parameters and feed them through a neural network. And we compute the spectrum of energies in the resulting quantum process and plot them. And although the inputs were harmonic oscillators that have linear spectra, when you transform them via the neural network in this way, you get these spectra that are no longer linear and they sort of level off. So you can cook up all sorts of models with different properties by doing this. Okay, I'm over time, so I'll just summarize. So the takeaway messages have all centered around these applications of neural networks to quantum mechanics and quantum field theory. I've told you that neural networks give you a powerful way of parameterizing random functions. I've described for you the things you need to confront if you would like to use neural networks to reproduce field theory correlators. So you need infinitely many parameters, and you need to take infinite parameter limits in a particular way, because different things can result. In the 1D setting, I told you that under these mild assumptions, any 1D field theory admits a neural net description in this particular canonical form. You can engineer the Osterwalder-Schrader axioms, and you can apply neural networks to these quantum systems presented as stochastic processes to engineer new processes that are still unitary or reflection positive. And there's lots to do. So I, again, did not discuss training at all, but given these deep neural net models, what you could do is imagine taking a set of target observables like correlators or a spectrum you want to match and train the neural network to reproduce those observables in a target theory. This would be interesting to look at. We have a conjecture in the paper, which is a math conjecture, that every reflection positive process can be realized as a deep neural net quantum mechanics with Markov inputs. This is interesting, I think, for kind of more of a stochastic process reason. And of course, the most important thing, which will be the subject of the follow-up work, is the hierarchy case. So the goal, the real long-term goal, is to construct interacting hierarchy field theories using neural networks. And in that case, you have to understand neural nets that give you honest generalized functions or distributions as opposed to ordinary functions. Okay, let me stop there, and thank you for your attention.
So initially in the introduction, one of the motivations you mentioned was that there are theories where you don't have even like Lagrangian or Hamiltonian description.
Mhm.
So here, when you're relying on this stochastic, stochastic process picture, I would assume that in a sense already tells you like what time evolution should be like, and that's in a sense like already assuming some type of Hamiltonian. Am I correct? Statement? And also, if that's the case, like how would you imagine going for describing theories which do not necessarily have Lagrangian?
Good. So yes, in the 1D case, it's true that essentially by this Fokker-Planck argument that I was giving, I was describing, for any stochastic process, you can find this Fokker-Planck, and then you can transform it to a Hamiltonian. So you always have a Hamiltonian description, which you can view as coming. I mean, if you know the underlying degrees of freedom, and you know canonical momentum and do a Legendre transform, you can always reconstruct a Lagrangian.
Right.
So in that case, yes, in practice, if you have one of these deep neural net quantum mechanics models, it might not be so obvious what's the explicit closed form. You can get a numerical approximation to the Hamiltonian, but you have no guarantee that the Lagrangian that would come from doing this procedure would be anything particularly nice. So the first statement I would make would be that as a numerical thing, this technique might be useful for engineering 1D models where it may be difficult or unpleasant to write a Lagrangian. The second statement would be that the motivation of understanding non-Lagrangian theories, I think, applies more to the higher dimensional case. Because the higher dimensional version of this story, you have no analog of this Fokker-Planck-ology that you would be able to do to take in a distributional neural network and explicitly compute Hamiltonians and Lagrangians and things like this, right? So for the higher D case, there's some hope that even non-Lagrangian theories you might be able to realize with such a presentation.
Sorry, so in higher case, the picture is not given by some stochastic partial differential equation, it's something different.
Yeah, no, so my understanding is that the stochastic process language really only applies to the 1D case, right? So in higher D, I should emphasize that we're not doing what's sometimes called stochastic quantization. This is a slightly different thing where you added another fictitious time. This is one way of doing higher dimensional field theory, if you like, by adding an extra time and allowing things to settle down in that extra time. In that case, you do use a stochastic differential equation, even for the field theory case. But what we're doing is not that. And Arthur Jaffe had some paper about 10 years ago explaining that there's some tension between stochastic quantization and reflection positivity, and you might not expect it to really be able to give you RP in many cases. So at least the straightforward generalization of what we're doing to higher D will not have any obvious connection to stochastic property.
Can we go back to the quantum mechanics slide that was a few moments ago that I asked a question about?
Oops, which one? This one or?
Before, yeah. So what if I insist that you use the same sort of neuron nonlinearity function for each K, as opposed to allowing you to take a general FK? Right, this looks to me like you allow yourself at each of the intermediate nodes to take different sigma K, what you were calling sigma before.
Yes.
Right, whereas in the first part of the talk, you said that there's this theorem that you could have done anything you like with some one fixed sigma.
Yes.
So can you rerun this quantum mechanics story having one fixed sigma? And if so, what would that be like? That would be very, very different from the way we sort of standardly do path intervals.
Yes. I think to do that, so you would modify this architecture slightly. If the previous example had a hidden layer, if you like, this has no hidden layer. It's one layer of neurons where you just have random theta k times a fixed function. They're not being fed into a hidden layer.
Right.
But if you generalize this to have one hidden layer and the same sigma, which changes these FKs,
Yeah.
That would be something like a Sebenko type theorem for quantum mechanics or stochastic processes. So something like that might exist. It's not the representation that we had, but you can imagine writing something like that. We didn't.
There are these like neural ODE PD type constructions which allow you to like solve a PD by evolving like the weights in time.
Mhm.
Do you expect this to be also useful for doing some dynamical quantum field theory simulations? But
It's a good question. Naively, I would expect that to be more useful for simulating classical field theory in the sense that in that case, the data that you have is actually the equation of motion, and you might want to solve for the future behavior of the fields given the data on an initial time slice. In our case, what we're doing is in some sense intrinsically quantum because we never speak about classical equations of motion and we're always computing correlators, right? So differential equations don't enter directly, at least the classical equations of motion don't enter for us, but you could imagine that maybe in some more sophisticated setups, if you want to study things like, I don't know, derivatives of correlation functions or ward identities or something like this, where maybe there is some differential equation that some observable satisfies, then indeed, maybe you could apply it to that case.
No. Can you include fermions and do computations?
Good, it's an excellent question. Jim has a PhD student working on this now. My understanding is that they are basically able to get fermions working. They're focusing actually on fermions in the field theory case, which is harder. So what I think a nice thing to do would just be to do supersymmetric quantum mechanics, just what we did here, but with fermions. We've not done that yet, but I think since the field theory case appears to be working and the work in progress that they have, that you should be able to do it. And that would be
So-
invariance.
So, and you can do computations, meaning that it's alternative to the usual sign problem, like Monte Carlo with fermions.
Yes, yes, since this is not, it's not the usual approach, right? So that was the motivation for including fermions precisely, because this is not anything like the existing techniques like lattice theory or any lattice field theory or anything like this where you have sign issues, right? It's an orthogonal approach.
I see the people wanting the room outside.
Okay,
so we
good.
should
Okay.
thank you again.